Hey friends, we're in chapter 6 and we're taking a look at linear equations and inequalities. And what we're going to talk about is a new concept. Basically, we're going to be graphing. At this point, we're going to be graphing lines, seeing where they intersect all over the place. That's pretty much the point of what we're going to talk about. We've got some vocabulary, a little bit extensive, but not too bad for you guys. And I know you can't see it, but it says graphing systems of equations. That's the name of section 6.1. Let's get started. So here's our vocabulary. The first thing that we're looking at over here, let me grab something. First thing that we're looking at over here is the concept of systems of equations. It's two or more equations being considered for shared solutions. So for instance, if I have this graph here and I have one equation, I graph it like that. The next equation, I graph it like that. These two equations could be considered for where they might be equal, and they are equal where they intersect, meaning they have the same xy value that satisfies both equations. So that, if this were like a real problem, xy would be the solution wherever point they intersect. So we're looking for solutions to systems of the linear equations by graphing. So we're going to be doing a whole lot of graphing in this section. Consistent, independent, and dependent are all kind of related. So you have a consistent system of linear equations if you have at least one solution. Now, if you have one solution, this is if you have one solution and it's consistent. So if it's consistent, meaning there's a solution, and you've got one solution, then that's called independent. Sorry for writing over the work. That's called independent. If you have a system that's consistent, meaning there's at least one or more solutions, and it's infinitely many solutions, we call it dependent. So one solution or infinitely many solutions. So consistent, you have to be independent and consistent or dependent and consistent, right? Now, inconsistent is not within this, so I'm going to actually use orange. Inconsistent is simply when you have a pair of linear equations with no solution. Can you guys envision what that would look like? What would a pair of linear equations that do not intersect look like? I heard somebody say it. Parallel. They would be parallel lines. So you know, in a case like this, if you have a linear system of linear equations and you've got parallel lines, you've got an inconsistent situation. There's no dependent or independent. It's just inconsistent. Yeah? Yeah? Okay. Let's go ahead and look at some examples. This first example, I had to employ Desmos because I needed a way to graph nicely. I don't think you guys wanted to see my shaky graphs, though you will before the end of the lesson. So here we have graphs. You see y equals negative 2x plus 3. That's red, so that's graphed here in red. The next equation is in blue, so forth and so on. And the question is down here. It says use the graphs above to determine whether the system is inconsistent or consistent, and if it's independent or dependent. Remember, the independent-dependent piece is only if you have a consistent graph, right? Inconsistent is just nothing to talk about. They're parallel. We don't talk about them. But consistent now can be broken down into two categories. So let's check it out. So right here we have y is equal to negative 2x plus 3. We can see negative 2x plus 3 is this red guy. And then we've got y is equal to x minus 5. X minus 5 is this blue guy. So when I look at just the red and the blue equation, or the red and the blue line, would you say, what category? Is it inconsistent? Is it consistent? Is it independent or dependent? Well, first of all, it's not inconsistent, right? Because we just talked about inconsistent meaning that we have parallel lines that don't intersect, right? So we do have lines that intersect. In fact, they intersect here. So we know that we've got consistent. So I'm going to write that down. First of all, this is consistent. Secondly, we need to now consider what category of consistent is it? Is it independent or dependent? Do you guys remember the definition? We just talked about it. It is independent, because independent means that there's one solution. We could scroll back, but I know you already wrote it down, so you don't need that. So this is consistent, independent. All right. This next guy, let's consider over here. Let's look at the graph. So we're looking at y is equal to negative 2x minus 5. I look over here. I see it's a green bad boy. And y is equal to negative 2x plus 3. Look over here. It's the red one. What do you notice? Well, first of all, their slopes are the same, and you can clearly see that their slopes are the same because we know when you have the same slope, they're parallel. So these are parallel lines, and clearly we talked about parallel lines. Remember the whole dance before? Ow, I hurt my elbow. That is inconsistent, people, inconsistent. inconsistent, right? That wasn't too bad. You'll probably see one of these on your test where it's already graphed for you, so make sure and keep a keen eye in terms of differentiating which equation refers to which line. We'll try to color code it for you. Let's look at this next one. So in here, in example, let's see if we can get more. In example 2, we're going to solve by graphing. So we're going to actually do the work. This isn't graphed for us. So we have y is equal to negative 3x plus 10 and y is equal to x minus 2. We're going to solve each system and determine the number of solutions that it has. If it has one, we're going to name the solution. So basically, we're going to see if the graphs intersect in one point. If it does, we're going to so we'll name it, right? So I've taken the liberty to color code this, purple graph, green graph, labeled this. I probably did not choose the best graph grid because I chose a really tight one. I didn't realize that y-intercept was 10, but it's in slope-intercept form. Let's graph it and see what we can do. So my slope is going to be negative. My y-intercept is 10, so notice I have a big dot here. My slope is negative 3, so that means go down 3, go to the right 1. And I know I've counted by 2s, but if you think about it, it's still the same thing. Because watch, if I go down 6, which is really 1, 2, 3, I've gone down 6 points, and then I go to the right 1, which is really 2, negative 6 over 2 is really negative 3 over 1. I'm just justifying people. So then this point is a part of the graph, right? Down 1, 2, 3 over 1, go down 1, 2, 3 over 1, go down again 1, 2, 3 over 1. The reason why this is okay for me to do is because I was consistent about the way I labeled both axes. So I can still do that. So now I'm going to try my best to draw a straight line like that. All right, so that's one graph done. So the next thing you want to do is graph the other graph. And so here my y-intercept is negative 2, so that's down here, because again I've counted by 2s, and my slope is 1 over 1, so I'm going to go up 1 over 1, but again I counted by 2s. It is okay for me to go up 2 over 2 because that resolves to 1, right? Rise over 1, go up 2 over 2, changing y, changing it. Yes, people, you know what I'm talking about. So up 1 over 1. And you can see that we have an intersection right there. All right? And the question is, and the reason why this is tight is because, yes, I know I have one solution that's good for this particular problem, but the question is, what is it? Right? What is that solution? So when I figure out what that solution is, if I plug it into both equations, it's a satisfier. And so as I look here, it's kind of midway between these guys and midway between these guys. It's looking like a positive 3 and a 1, let's say. Let's see what happens. So I think that's positive 3, 1. I can check and confirm it by plugging it in. When I put a 1 in for y and I put a 3 in for x, I do indeed get a satisfied equation, right? Because 1 is equal to negative 3 times 3 plus 10. 10 plus negative 9 is 1. That's cool. Let's check it over here. 1, is that equal to 3 minus 2? Sure enough. So now I have my answer. So my solution is indeed 3, positive 1. So that's my solution for this first one. Hopefully I'll be able to graph this a little bit better. All right, so color coding again, we don't have these in slope-intercept form, so let's put it in slope-intercept form, remembering that is y equals mx plus b. So we're going to do that here. We get negative y is equal to negative 2x minus 1. How did I do that? I moved this guy over here, which gave me a negative 2x. This is still negative. I'm going to multiply both sides by negative 1 or divide by negative 1, whatever's floats your boat. Y is equal to a positive 2x plus 1. The next equation, our blue equation, we're going to do something similar. I am looking to move 4x to the other side, so I have minus 2y is equal to negative 4x plus 6. I need to divide everything by negative 2 in order to fully isolate y. Y is equal to negative 4 divided by a negative 2 is a positive 2x. 6 divided by negative 2 is a minus 3. So right now, we've got these two equations. I hope somebody out there is saying, Dion, it's not going to work. Well, it works, but I hope you see that the slopes are the same. And therefore, when we have the same slope, we know we've got parallel lines. So our situation is going to be inconsistent. But for the sake of graphing, let's do what we do. Think I'm got orange there, good. So I'm going to go, my y-intercept is a positive 1. My slope is 2. So I go up 2 over 2, down 2, back 2. And that wasn't right. That last one wasn't good. But these other ones are perfectly fine. And this is my graph. And then I do the same thing for this blue equation. My y-intercept is negative 3, but my slope is exactly the same. So you realize that these equations, these lines will never meet. So in this situation, we have an inconsistent. So this one was inconsistent, right? Because there was no solution. And this one over here was consistent and independent. Independent. All right. So that's what we have. One more example, friends. One more example and we're done. Do I have another example? I believe I do. I don't see it, but I'm going to make one up for you. Give me a second. Okay, finally, I found it. So here's our final example, example 3. It says write and solve a system of equation. We've got Joe and Josh, and each of them want to buy a video game. Joe has $14 and will save $10 per week. Josh starts off with $26 and saves $7 a week. And how many weeks will they have the same amount of money? So we're looking for the time when they have equal amounts of money. I think it makes sense to write an equation for both of them. Let's check out Josh. We recognize that Josh has 26 bucks and saves $7 a week. You guys are really good at these kinds of equations. So for Josh, I should use purple. For Josh, we're going to have y is equal to 7x, where x represents each week, plus 26, the amount he starts off with. Similarly, we can write an equation for Joe with the same logic. Y is equal to the $14 that he has plus 10 times x. And so we end up seeing that we've got a slope and a y-intercept. My graph, I was really trying hard to fit everything. You see this little zigzag line? The zigzag line says, hey, I'm not starting at 0. And then boom, I start at whatever number is most convenient. So I've chosen to start at 14, which is Joe's y-intercept, right? And then so we see that Joe gets $10 a week. So I'm going to put that graph together. So looking just at Joe, we see that he starts off at $14, add 10 more dollars. He has 24, add 10 more dollars, 34, 44, 54, and that'll be 64 all the way out there. And so the line that I'm going to draw for him slowly and patiently and crookedly looks like that. All right, let's draw a line for Josh. So Josh starts off with $26. This is 14. This is 18. This is 22. This is 22, 24, 26 is right here. So we're starting off with $26 and we're going to add to $26 $7 each time. So let's take a look. So what I did is I basically rocked the same thing that we do with the slope, but it's pretty hard to do here. So what I did is I said, okay, well, we start off with 26. When I add 7 to that, because that's how much we're adding per week, 26 plus 7 gave me 33. Then I add 7 to that, and I got 40, and I added 7 to that, and I got 47, and I add 7 to that, and I got 54. So finally they coincided, and if I add 7 to that, I get 61. However, what I was looking for is the solution, the place where they both intersect, and so they both intersect here, which is the point 454. So what does this mean? This means that after 4 weeks, right, they both would have the same amount of moolah, which is $54, equal amount. So that's when they would equal. And then the guy who's saving more, obviously Joe, will supersede and will surpass. I hope that makes sense to you. I look forward to talking to you guys. Even though graphing is painful, it will get easier and we'll have more elegant ways to solve systems of linear equations. Can't wait to talk to you. Take it easy. Have an excellent day. Bye-bye.